Welcome back to Office Hours with Dr. Clark. Today we're going to be looking at Lewis structures. This is often confusing parts of general chemistry, but it's such a foundation, no part for organic chemistry. Okay, so first we have to understand valence, and we have to understand octet. Well, right, so valence, outer electrons, responsible for bonding. Octet rule, atoms need an 8 outer electrons for stability. Some are okay with less. Example, H. That's a bad looking H. H, boron, etc. So your period 2 elements can never have more than 8. Period 2, period 3. If you're looking at like aluminum, silicon, etc., can have greater than equal to 8. Sample phosphorus, sulfur, oxygen, carbon, etc. Right. So we'll see some exceptions to the octet rule in some structures. So when we're looking at Lewis structures, we have to talk about electronegativity. Electronegativity. That is the attraction of atoms in, well, let's say, on the covalently. Covalently shared electrons. So what we mean is, if we say we take an O and an H bond, right? Very popular bond. Oxygen is more electronegative, so the electron density is going to be more dense around oxygen compared to hydrogen. Okay. So we said there is a partial negative charge on oxygen and partial positive on hydrogen. This sets the stage for polarity. So we've given atoms arbitrary values of electronegativity. For example, fluorine is the highest, I guess, 4, oxygen 3.5, nitrogen 3.0, chlorine 3.0, potassium 0.9, carbon 2.5, H 2.1. So we can use these numbers to see, okay, if I have a bond between, say, C and H, I'm going to have most electron density on carbon. However, the difference between carbon and hydrogen, so we call that delta En, is equal to 2.5 minus 2.1. That's 0.4. So we consider anything less than 0.5 to be nonpolar, meaning there's not a preference, a big preference for electrons to congregate around a specific atom. Now you can see carbon has slightly more preference, but it's not enough for you to call it a polar molecule. So 0.5 or greater is considered polar. And, roughly if we get to 0.2 or greater, you consider an ionic bond. So your metal, non-metal bonds are going to be such a discrepancy in electron density that the electrons are going to be no longer shared. It's going to be transferred from the metal to the non-metal. Okay. So if we look at the OH bond, oxygen is 3.5, hydrogen is 2.1. Our delta En is 1.4. So that is a very polar bond. Right? And we talk about how to judge polarity of an overall molecule in a different video. So for now, let's talk about Lewis structures. So the first thing is we need to count valence electrons. So you can look at your periodic table for that. If you look at the column numbers, it could tell you what the valence. Now we're going to focus on columns 1, 2, and then 3 through 8, right? We're not going to mess with the middle, the transitions, okay? So we can tell the valence very simply by looking at the column numbers. And the next thing is we want to put least electronegative in center. However, we never, ever, like ever, put H in the center. Okay, because hydrogen only wants 2 electrons. It just wants 2 electrons in its outer shell to be happy. So if you put that in the center, it's going to get more than 2. It's not going to be happy. So you always put it as the outer, even if it's at least electronegative. Okay. Another rule is you fill octets for more electronegative elements first. Then double bonds, triple bonds needed if outer elements are satisfied, but central still lacking. So we'll look at some examples. And then for charges, charge molecules, like your polyatomic, if it's negative, add to valence, sum. If it's positive, subtract. So let's look at some examples. So we're going to take simple binary molecules like, let's say, fluorine, F2. So valence of fluorine is 7. So we have 2 times 7, that's 14. Two, 4, 6, 8. So now we have 2, 4, 6, 8, 10, 12, 14. So we have 14 electrons, so we can't use any more or any less. And then we can draw every pair shared. We can indicate with single little line, call it a single bond. Call it a single bond. So, so each fluorine contributes an electron to the shared pairing in the middle here. Okay. Let's look at, say, carbon dioxide. So we have carbon, that's 4. 2 oxygens each having 6. So that's 4, 12, that's 16. So we put carbon in the middle since it's the least electronegative. And we're not going to worry about shapes right now until a different video. So then we start making, so notice we're always putting electrons in pairs. So just taking care of the oxygens first. And you'll notice that, so we use all of our electrons. We have 16, but carbon is still not happy. So now is where we form, we take, to erase oxygen. So we take a pair from the oxygen, put its shares. So now carbon has its 8, oxygen also still has 8, but now we have 2 double bonds. And we draw, so each pair of the double bond represents a line. So we call this a double bond. Okay. Let's try something with a triple bond, HCN. So 1H, H has 1 valence electron, carbon 4, nitrogen 5. So we have 10 total electrons. So put carbon in the middle again, not H, because we never, ever, ever, like ever, with H in the center. So we take a nitrogen first, 2, 4, 6, 8, and then like I'll put 2 between the carbon and the hydrogen, since middle hydrogen wants 2. But my carbon is not happy. It has 4. So I'm going to carefully, without erasing my nitrogen, remove 4 electrons. So then I have A, C, triple. I have a triple bond between the C and the N. So I call that a triple bond. This is how you do your Lewis structures. Let's take something that has a charge, like sulfate. So your polyatomics, they do have charges, as we know, and they actually are held together by covalent bonds, even though they have an overall charge. So sulfur is 2.6, electronegativity, oxide is 3.5. So put sulfur in the middle. Oxygen is around, so then we have 1 sulfur, that's 6, 4 oxygen is 6, 4, so we have 30, and we have a charge of 2, so we're gonna add 2, so it's 32. 2, 4, 6, 8, 10, 12, 14, 16, 15, 20, 22, 24, 26, 28, 30, 32. So I always like to write in my lone pairs or unshared pairs. Right? So we call these unshared pairs or pairs. So we talked about if you have a charge, we talked about um yeah, lone pairs, double bonds, triple bonds. So now let's look at something like BCl5. Talk about like when you have variations from the octet rule. So we have one phosphorus, that's five. The chlorine, there's five chlorines, each having seven. That's five. That's 35. That's 40. Phosphorus is less electronegative than um, chlorine, put that in the middle. You find that you don't find halogens in the middle very often. Because halogens, they are totally satisfied with just one bond and three unshared pairs. So they tend not to want to be in the middle. They're less stable when they're in the middle. Whereas your phosphoruses, your sulfurs, those tend to be okay being in the middle, but they can also be outer atoms too. So then we take care of the chlorines first since they're more electronegative. So so I'm missing the chlorine. So I have each chlorine having three pairs. They notice phosphorus has 10 electrons. And phosphorus, given period three, can put those extra electrons above the eight in d orbitals because your period three atoms have d orbitals that it can use to accommodate extra electrons. Now, what about something like beryllium chloride? Beryllium is a metal, but it can form non-valent covalent bonds. So beryllium is two, my two chlorines, seven. So we have 2 plus 14, 16. Beryllium is going to be in the middle. It's a metal, so it's definitely going to be lower than chlorine. Sorry, electronegativity. Electronegativity, I didn't mention, it varies. And let me just kind of put a quick aside here. Electronegativity increases left to right, decreases top to bottom. All right, so it's an increase, it's a decrease. All right. So your noble gases aren't electronegative because they're not reactive, but your halogens are, the most, and fluorine being the top. All right, so your metals are going to be low, high, sorry, and then high. All right, so electronegativity kind of increases diagonally towards the right. So anyways, you can tell, generally which is going to be less electronegative without, knowing the numbers. So I have my 16. So I fill my chlorines out. And beryllium gets, a couple pairs. And beryllium is totally content with just having two bonds. We don't need to make double bonds to make it actually it's less happy when it has double bonds. Okay. So that is how we draw Lewis structures. So in the next video, we're going to talk about some more details like formal charges, resonance, and shapes of molecules. All right, until next time, Officer Dr. Clark.